Hi, everyone. Can everyone hear me? Okay. Thanks, Lydia. Thanks, everyone, for being here. I'm very excited to present this work. We'll start with some high-level motivation. So we all know that kind of algorithms are being used for high-stakes decisions, but they can exhibit some sort of undesirable biases. These are some headlines I'm sure you might have seen from the past decade in various applications. And so this has, these kind of bad outcomes have motivated a lot of work from the algorithm machine learning community to try to kind of fix these algorithms. One approach has been to define like notions of fairness, such as demographic parity. But one question you might have is, okay, do these fairness notions, we can think of these fairness notions kind of as an intervention. But the question is, okay, are they actually helping like solve this like underlying issue? One way in which one limitation of some of these notions is that they're defined in a static context. It's like a one-shot problem, which cannot like inherently account for long-term impact. Like how does an intervention impact the long-term of like some person or a group of people? So this kind of motivates the study of more dynamic models. And that's kind of the high-level motivation of our model. Okay, so in our work, we're going to focus on one application, which is like hiring and school admissions as an application. And we're going to focus on studying one set of dynamics. Okay, the dynamics is that a firm is better at evaluating applicants from groups it has hired from in the recent past. Okay, so we'll just be studying these type of dynamics. We'll formalize this mathematically. And we'll be building off the literature on statistical discrimination. Okay. And so first I will describe this classical model by Phelps, which is a static model of statistical discrimination, and then we'll turn it into a dynamic model. Okay, so this model, there's applicants. Each of them have a scalar skill, which is drawn from a known prior, normal 0, 1, and each applicant is associated with a group, A or B. The firm observes not the true skill, but the skill plus noise, where the noise is zero mean, but the variance depends on the group of the applicant. So the variance kind of represents how well the firm can really observe the skill, kind of evaluate the applicant. And so the firm wants to hire people with a high skill, so they can compute an applicant's expected skill given the observation, which has this formula. And you can see that the variance is at the bottom. So if the variance of the noise is really high, then this term goes to 0. Okay. And so you can see that if you have two different groups with two different values of this variance, then even though their underlying skill might be the same, the observed skill by the firm is different across these two groups. And therefore, if two groups have a different value of this parameter, then you'll get different outcomes for these groups if the firm is making decisions based off of this value. Okay, so that's the kind of classical model. And so we'll build on this. And we're going to essentially make this noise variance to be changing over time. Okay, so the example you can have in your mind is that you can think of the groups as like people from students from different colleges, let's say, and every time step is like a year of like new grads. Okay, and a firm is like hiring, let's say, for one group from like, let's say, the University of Pittsburgh. Okay, so here's the model. So P is just like, so here we're thinking about it for just one group, one firm and one group of applicants. Okay, P is just the group size, how big the group is. We're assuming the hiring rule is that the firm will hire all applicants whose expected skill is higher than some exogenous threshold tau. Well, okay, and then sigma 1 is the initial condition, the initial noise variance. And then QT is the percentage of people hired at time t according to this hiring rule. And the main dynamics is this one. The noise variance updates so the noise variance in the next time step is h of p times q. Okay, so p times q is the mass of people hired at time t. You can think of this as the number of people you hired at time t. H is a decreasing function, which means if you hired more people this time step, then at the next time step, your noise is smaller, which means you're better at evaluating. Like the noise is a decreasing function. So you're better at evaluating if you hired more people in the previous time step. Okay, and so this is the dynamics that formalizes the idea that a firm is better at evaluating applicants if they've hired people from that group in the recent past. Okay, so for this talk, we'll assume that h of x has this particular functional form, 1 over x, but in the paper, we consider several other variants of this function. Okay, so let me just visualize one time step of our process. The noise variance starts at some sigma, and then this induces some distribution of this inferred skill for the group, and then the firm hires everyone whose inferred skill is above this threshold, and then the people who are hired, that's just the percentage of people in this shaded region. And then at the next time step, we just use this function to update our noise variance. Okay, and then this cycle happens over and over again. So we're going to define the function that maps the noise variance at time t to t plus 1 as f. And so we just have to understand how f behaves, because that's how we want to understand the long-term impact. Okay, we need to understand how f of x compares to x, right? Because if f of x is larger than x, this means the noise variance is increasing, whereas if it's less than x, it's decreasing. Okay, so here's one example of what f of x might look like. Okay, so here there's actually kind of two different regimes. If you start in this regime, then f of x is always larger than x. So here, your noise variance continuously increases over time, and you eventually diverge to infinity. Okay, whereas if you start in this regime, you can see that f of x is less than x, so your noise decreases over time, and it actually converges to this point. And same if you start here. So actually, in this regime, your noise ends up converging to this finite outcome. So there's only two possibilities for where you can end up. You can either end up your noise going to infinity or ending up at a finite state. This is actually a bad outcome. This is what we're going to call an inactive steady state, because if your noise goes to infinity, you actually end up hiring nobody from that group in the long run. Whereas here, you end up hiring a finite number of people at every time step. Okay, so basically our main result is that this f of x function has this shape, has this like kind of convex looking shape, although this function is actually not actually convex. So yeah, so this is kind of the main result. And so what are the main implications of this result? Well, so again, this was just for one group of applicants, but now let's think about two groups. And essentially, the outcome depends on where you started, right? So if you have group A and group B, and for some reason they started at different points some while ago, and then over time, and let's say they started at two different sides of this threshold, then over time, this initially small disparity kind of exacerbates over time, and eventually no one from group B is hired, whereas the firm will continuously hire from group A. So this kind of says that, provides evidence of why historical disadvantages can persist and exacerbate over time, leading to drastic long-term disparities. Okay, let me just kind of skip the literature review for time. But now, like, we can think about interventions. Like, okay, now, like, how can we help a group? So maybe we have a group that's kind of in a bad state, and like, okay, like we maybe want to help them. We can help them by reducing the noise. So there's different ways to do this. Like maybe we can hire more applicants from that group, or we can spend more time evaluating them. Maybe we spend more time interviewing applicants from that group so that their noise variance is reduced. But mainly, I want to say that we want to get the noise variance of the group below this threshold. Okay, so if you have like a mild intervention that only pushes the group to like slightly lower but doesn't cross the threshold, then whatever intervention this was, once you lift the intervention, the group is going to go back to the bad state, right? Whereas if you have a more drastic intervention, even if the drastic intervention is a short-term intervention, if it pushes the group like below the threshold, then once you lift the intervention, that's fine, because the group will actually naturally head to this like good state. Okay, so essentially drastic interventions, even if they're short-term, are better than milder or longer term interventions. Okay, and kind of trying to relate this to kind of the real world interventions, you can think of affirmative action as like an intervention that was in place for a long time, which was recently lifted, lifted by the Supreme Court decisions. And some preliminary data show that after this intervention was lifted, a lot of colleges has noticed a decline in Black enrollment. So, thinking about this in the context of our model, we can think of perhaps this was an intervention where once we lifted it, like a group might go back to a bad state. But obviously, this is a very complex problem, and I'm not saying our simple model like explains everything, but this is kind of like, it might explain parts of what's happening. Okay, so lastly, our results show that smaller groups are actually worse off in two ways. It kind of formalizes the statistical reason why smaller groups are worse off. Like the threshold is more tight for smaller groups, and even when the group is at the good state, the percentage of people hired is actually even smaller for the smaller group than the larger group. So actually, even when both groups are in the good state, like the smaller group, there's a fewer percentage of people hired. So like even like demographic parity isn't satisfied, even when the two groups are both in the good state. Okay, so that's those are the main kind of results of the paper. But in the paper, we have several extensions, like some simulations and robustness checks. So refer to our paper for more details. And yeah, thanks so much.
Thank you. Yeah, we can take a couple of questions. Yeah, one question here. You can just shout it out. Yeah.
Smaller groups, right? So I guess my question is, do you assume in your model that you can sample equally from both the groups to get that drastic short-term intervention?
I'm not sure what you mean by sample. Like in our model, we're assuming that firms use this particular hiring rule where people, you hire everyone above a threshold. In terms of interventions, I didn't go, we don't go into like what exactly are the interventions. It's like, any intervention that can reduce the noise, right? So this could just be explicitly hiring more people. That could reduce the noise in the next
right. So I guess for hiring them, I'm assuming there's enough applicants that you can hire from the groups which need a bigger intervention to get them to the converging.
Right. Like hire a higher percentage of people from that group.
Right.
Yeah.
So like there's enough population.
Yeah.
Okay,
yeah.
Got it.
Yeah.
Thank you.
Over here.
Thank you. So you have this H function that's updating the variance, but presumably firms have continued experiences with the workers they actually hire. Can you update the variance in this model using information revealed during the tenure of the workers? Like they could be drawing new signals and the firm can now be averaging over that noise over time. Do you think it's feasible to keep the logic of the model, but like incorporate the fact that employers and employees learn about each other?
I mean, I think like, I guess I'm not like, do you mean employees, you learn more like during their, like, I think like the dynamics is trying to model like, oh, like if you hire people from time T, then you learn more about that user, about that applicant because you hired them. And that's why the noise variance reduces at the next time step. And maybe even it'll be further reduced the time step after that. But we just model like kind of this one step just for simplicity. But yeah, I think like, so it's kind of like modeling a lot of things in there. And then, but we do a lot of robustness checks in that like, oh, maybe the noise variance is a function of like multiple previous time steps or like different functional forms as well. So we've considered like different variants. Yeah, thanks.
Okay. Yeah, we can take one last question.
Hi, Jackie. Thanks for the great talk. So what if the tau is different for different group and what if the tau is changed over time? like exogenous threshold?
Great. Yeah. So we assume that tau is exogenous. So we consider an extension in the paper. So here in this model that I presented, the groups are actually not interacting with each other, which is actually kind of unrealistic because in reality, the firm might have just like, want to hire the 10 best people. So we have an extension where the groups are competing. And so tau is endogenously chosen as like, the top, 10 people from either group. So we consider like an endogenous tau as well. Yeah.
Okay, great. Thanks so much, Jackie. Yeah.